Yeah, thank you very much. Thanks a lot for the invitation. I already told the organizers, but I want to put this sort of officially out here. I really appreciate you guys organizing this, sort of making all the videos available. Somehow for family and teaching reasons, it's really difficult for me to join in all of the talks, but I've been constantly watching them in the evening and enjoying them a lot. So really, thanks a lot for doing this. And thanks for inviting me to speak. So I want to talk about a relation between K and L theory of C-star algebra. So this is a series of works that I've been working on for some time, and I want to give you a somewhat historic overview of sort of what happened and sort of how things developed from my point of view. And so the basic setup is as follows. So the claim is that there exist, it's just something for now I want you to take as a fact. So there exist at some structure lag symmetric monoidal functors. Okay, so what is it we can do? We can look at C-star algebras. And in the beginning, C-star algebras will mean complex C-star algebras. Later, I'll also be interested in real C-star algebras, and I'll have the audacity to call real C-star algebras R-star algebras, just to, sort of to notationally distinguish the two. So there is this functor that we've been talking about, or I mean that sort of was the content of a number of talks, which is the topological K-theory functor. Let me just write that as K. So there's going to be no appearance of algebraic K-theory, I think, in this talk. So every K is a topological K-theory. And then there's another functor that exists. So I can take C-star algebras, and a C-star algebra in particular is a ring, and this ring comes with an involution. And then there's some algebraic property and maybe some topology that's uniquely determined by the algebra or whatever. But regardless, any C-star algebra gives rise to a ring with involution. And on rings with involution, there is a second functor that people care about, and that's called L theory. So this is this L theory. Let me say this. This is it's in some sense built from, in a suitable sense, from studying some kind of higher width groups of unimodular forms. Okay, so instead of looking at projective modules, as you would do in topological or algebraic K-theory, you look at projective modules, say, equipped with a unimodular form. And then this L theory is a process, or these L groups somehow in the easiest instant are just given by width groups, and these width groups would be obtained by looking at the monoid of all such unimodular forms, and then dividing out the submonoid generated by things that contain the Lagrangian. That's just, I don't know, maximally half-dimensional subspace on which this form vanishes. It's not too important for now. I think for the time being, I just want to say there is some functor called L theory, whose homotopy groups are all explicitly described in terms of width groups of forms and what are called formations in general. Let me just, for sort of a motivating thing where this comes from. So for instance, width groups of fields, apologies, width groups of fields, they're sort of closely related to number theory. So there's a theorem, for instance, that says that whenever you look at the width group of symmetric forms on a field, it comes with this filtration, the sort of fundamental filtration. There's a certain ideal in it, whose powers you can look at, and this associated gradient for this ideal filtration can be described in terms of Galois cohomology of your field. And so somehow these width groups have a close relation to number theory. But there's a second way in which in these L groups or width groups canonically appear, and that's in surgery theory. So in surgery theory, and maybe let me be specific here, that sort of width groups of quadratic forms rather than symmetric forms, quadratic width groups appear as surgery obstruction groups. Yeah, so sort of topologists care about these L groups because they care about surgery theory. And if you want to sort of perform surgery theory to maybe prove that a space that you care about is homotopy equivalent to a manifold, at some point there's going to be an obstruction of performing surgeries. to constructing a homotopy equivalence, and then these obstructions lie in L groups or width groups. So there's a plethora of applications of this kind. And so one of the motivations was the following, that well known that associated to these functors, there is something that I'll write like KG, an equivariant K-theory functor that I'll evaluate on a classifying space for a family of subgroups in the exact sense that Uli described. So I think Uli would have written this maybe as something like a colimit over maybe the GF orbit category of some functor K underline. And this is there's an assembly map that tries to compute the K-theory of the reduced group C-star algebra, perhaps. So that's the content and the question of whether or not this map is an isomorphism for suitable families F, perhaps the family of finite subgroups, is the content of the Baum-Kohn conjecture. And okay, now I guess most of the people in the audience know that the Baum-Kohn conjecture can be phrased without referring to any spectrum things, but this perspective is going to be helpful. So this Davis-Lück approach to the assembly map for the topological K-theory functor yields an assembly map that's equivalent to the Baum-Kohn map that you construct purely from KK theory. And there's an analog that you can do for any ring with involution R. There is an equivariant L-theory spectrum, LR, upper G, that you can also evaluate on EFG. And there is another assembly map. So maybe I always call this the Baum-Kohn map, and this the Farrell-Jones map. This is sort of the content of the L-theoretic Farrell-Jones conjecture, which tries to compute the L-theory of the group ring RG. And somewhat was known that these two, that these two, they ought to be related. And in at least a survey about assembly maps that was written, I believe, by Wolfgang Lück and Holger Reich. I'm actually not so sure anymore, but okay, some survey also outlines sort of why that should be so and what this exact thing is. But point being is that the details of a construction of this kind were just not really available at the time being. And so the starting point of this whole discussion was to make a rigorous comparison between the K-theory functor and the L-theory functor when restricted to C-star algebras, as to make precise in what sense these two assembly maps are related. One reason to believe that these two ought to be related can be expressed in terms of the following theorem that is partly due to Karoubi, Jonathan Rosenberg, and also Miller, that says the following. So if A is, maybe let me say unital C-star algebra, the unital is not so important for now, a unital C-star algebra, then, I mean, I guess a number of things hold. So on the one hand side, L theory, so the nth L group of A is naturally isomorphic to the n plus second L theory of A. So L theory is two periodic, as is topological K theory, and moreover, there are natural isomorphisms between the zeroth K theory group and the zeroth L theory group, as well as the zeroth, the first K theory group and the first L theory group. Okay, so in other words, because both of these theories are two periodic, really all of the homotopy groups are naturally isomorphic. Yeah, all L groups are naturally isomorphic to all the K groups. This is the content of this theorem. Let me give you one small piece of somewhat of a warning. So there are two different ways of trying to think about L theory, or width groups of forms. And the point being is that I can think about width groups of forms on projective modules, or I can think about width groups of forms on, say, stably free or free modules. Yeah, and this is just not just not the same thing, and both are somewhat relevant in surgery theory. Somehow in surgery theory, you'd really always be interested in the L groups that are based on free modules or stably free modules. Some of the projective ones are not quite as relevant. And so in this isomorphism, it's important to work with projective L theory. In this isomorphism, it's important to work with free L theory. And it just happens to be that for a complex C-star algebra, free L theory and projective L theory happen to be isomorphic in degree 1. So this is a bit of a, I mean, it already indicates that something interesting is going on. Yeah? I mean, in some sense, the natural way of relating K1 with L1 uses free L theory, whereas the natural way of relating K0 with L0 uses projective things. Okay, this is just a matter of fact. This is so. And I would refer to, okay, I mean, I can give somewhat, I wanted to make an indication for why K0 and L0 are isomorphic. And I wanted to skip why K1 and L1 are also isomorphic, but there is a very nice paper by Jonathan Rosenberg called Analytic Novikov for Topologists. So it's he tries to explain to topologists the picture of the Novikov conjecture that the analytic people have. And in this paper, he describes this isomorphism K1 to L1. So I invite you to have a look at that. So a small idea for the n equals 0 case, idea for K0 isomorphic to L0. And I specifically want to do this historically so you can understand a bit of what some of the confusion that at least I and I think a number of people shared this confusion had. So the idea was to do the following. So pick a projective module and a form, a unimodular form on a phi unimodular form on P. So that's an element that represents an element in L0 of A. Yeah? And the idea is to do, well, just Sylvester's theorem over C-star algebras. What you want to do is to say, well, by spectral theory, I can take this unimodular form and I can decompose it into a part in which it is positive definite and a part on which it is negative definite. So by spectral theory, we write P phi as P plus phi plus plus P minus phi minus, where phi plus is positive definite, phi minus is negative definite. And then you use that if P is projective, then over A, over a C-star algebra A, then there exists an essentially unique positive definite form on P. Essentially, you think about P as a Hilbert C-star module, and then the scalar product you have on it is the thing, and the same as any other positive definite form is just isometric to that one. Okay? So really, what you do is you write it as P plus, and then this canonical guy associated to this. Okay. And here you already see that really you're using sort of projective modules, because even if P happened to be a free module, then this decomposition really only allows you to decompose it into two projectives, not into two free ones in general. So you cannot sort of easily make an argument for free L theory in the same, like in the literal same way. Okay, so this is one idea that you can have. So another perspective that I wanted to say very briefly only, there is a series of papers. There exists a series of papers called Mapping Surgery to Analysis. I think it's 1, 2, and 3. So these are papers by Hickson and Rowe, which had the intention to constructing a short exact sequence of C-star algebras whose associated long exact sequence in K theory mimics the surgery exact sequence from geometry and receives a map from the surgery exact sequence. Okay, so again, I'm stressing this for the reason that I say in this picture, somehow what looked to be the thing you do is you take an element in L theory and you split it up into two pieces. You get something in K theory. And also from this perspective of mapping surgery to analysis, it looked like you want to map L theory to K theory if you want to have a comparison of these two things. Huh? Okay, so let me give you a couple of remarks about sort of what was known and or expected. So it was well known, and I'll indicate a bit why that is. It was well known that the K theory spectrum and the L theory spectrum are not equivalent as spectra. Yeah. So although their homotopy groups are naturally isomorphic, the spectra are well known not to be isomorphic. And I'll indicate later why that is. So in particular, it was clear that, you know, it cannot be true that L theory and K theory on C-star algebras are just equivalent functors. If you think about them as spectrum valued functors, it's just not true. And it was expected that, oh no, sorry, this was not expected. This was also well known. Was well known, although somewhat, I mean, I don't want to step on anyone's toes, but I had the impression that maybe the details in this were also somewhat sketchy. Well known that for fixed C-star algebra A, even an R-star algebra, so a real C-star algebra, that there exists an equivalence K of A equivalent to L. Oh, sorry, I should write this differently. So after inverting 2, yes. So if you throw out all the 2 torsion problems, then these spectra were sort of known to be equivalent for fixed A. That's, I think, what belief was known, and it was expected, at least that's what my recollection is, what Wolfgang Lück, my advisor, told me when he gave me this problem as part of my thesis. It was expected that there exists a natural map that kind of looks like a signature, as does this thing, right? I mean, sort of splicing up P into P plus and P minus, and then sending this form to the difference of these 2 projective modules. That is a signature. So if you do this over R, this is literally the signature. And so the idea was there might be a signature map that goes from the L theory of A to the K theory of A, and this map becomes an isomorphism when I invert 2 after inverting 2. Yeah? Sort of an expectation that was around. And let me just sort of, for, again, historical reasons, tell you that at the time, this didn't seem completely implausible to me for the following reason. So, I mean, you can wonder, how could you ever prove such a statement? And one absolutely reasonable way of proving such a statement is picking a model for L theory of A and a model for K theory of A and writing down the map. This is, I don't know, that's not an absurd way of doing it. It's not the way we're going to do it, but this is a way you can try to prove this. And then it did seem natural to me that this should go in this direction, because if you think about any model that you know about for the topological K theory space or spectrum, then it's a very continuous model. Yes, it's, I don't know, the things are maybe built on configuration space type things. A very continuous model. Whereas all models for L theory that I'm aware of, or that I was aware of at the time, are very combinatorial and really write down a simplicial set, essentially, some simplicial complex. And it just seems more natural to construct a map from something combinatorial to something sort of very continuous than the other way around. But okay, so that is, I think, a summary of what I thought at the time, somewhat the expectation is. And the theorem that I proved together with Thomas Nikolaus, and was, I think, published in 2018, says the following things. Let me just do it one way at a time. So there is a unique laxometric monoidal transformation which goes from little k to L. Now, little k is just the connective cover of the topological K theory functor. Yes, I just don't take the periodic thing, but only its connective cover. So there is a unique lax-symmetric monoidal transformation between these two functors. B, this given, let me call that tau, this transformation. So this transformation tau, if I evaluate it on a given algebra A, then it gives me a map from the K theory of A, connective, say, to the L theory of A, and this induces an isomorphism on pi 0 and pi 1, as is sort of compatible with this theorem, yes, that says K0 and K1 are naturally isomorphic. The statement is there is a natural transformation between these two functors, which on pi 0 and pi 1 induces an isomorphism, but this map does not induce an isomorphism on pi 2, turns out. Yeah? The groups are isomorphic, but the map is not an isomorphism. I think you're all well aware of maps between isomorphic groups that are not isomorphisms. The prototypical case that appears here is the map times 2 from Z to Z. Sort of just the way it is. Okay, so this is something that you have. In particular, what you can maybe improve this upon that, if you take this functor and you invert 2, then in fact, it induces a map on the periodic versions. Yeah, so recall that's really somewhat of a property of this transformation. This periodic thing is obtained from the connective thing by inverting the bot element. And so it's really a statement that after inverting 2, the bot element is sent to something invertible. That's a property of the thing. The statement is this map doesn't send the bot element to something invertible, but if you invert 2, then it does. So it induces a map from the periodic version of K of A with 2 inverted to L of A with 2 inverted, and this map is an isomorphism. So in some sense, a version of what was expected is true, but sort of in a different direction. Yeah. So there is something like an integral map between these two spectra, but you have to pass through the connective cover, and you have to map from K theory to L theory instead of the other way around. And then this map exists, and if you then invert 2, it induces this isomorphism that was previously known for a fixed A, but naturally in all C-star algebras, and naturally sort of as a functor with values in the infinity category of spectra, not maybe the homotopy category or something of that kind. Okay?
I have one question. So if one inverts the image of the bot element, does one invert 2?
Yes. So the statement is, like, maybe add this, I should add this here. So if I evaluate tau on the complex numbers, it's a map from what the topologists call little ku, that's just K of C, and maps to L of C, and it sets the bot element to 2 times generator. Yeah, that's a computation you have to make, and this computation is in similar spirit as the computation that I possibly will indicate later for why this map induces an isomorphism on the pi 0 and pi 1. Yeah. So somehow these there are really sort of different steps in this thing. The one thing is just constructing something, and then the second part is analyzing the properties of the thing that you've constructed. And analyzing these properties is somewhat of a computational thing, whereas the existence is somewhat of a formal thing. And I should maybe highlight that, I mean, as you see here, KK theory hasn't entered the picture, yes? I mean, I'm just talking about functors on C-star algebras, K theory and L theory, and I'm relating the two. And this is sort of in similar spirit as in Uli's talk in this week's conference, right? Where he was trying to explain how to compute maybe the K theory of a cross product in terms of things that, I don't know, can be phrased purely without ever talking about KK theory. But he used sort of the existence of the KK category and the equivariant KK categories and certain structures you obtain from this to give an interpretation of what it means for these maps that make perfect sense without ever talking about KK theory, sort of to be isomorphisms or so. And the way I touched sort of this homotopical approach to KK theory was exactly in this fashion. I just wanted to use KK theory to prove results about the relation between K and L theory of C-star algebras. And somehow none of these statements involve the existence of KK theory. It's really used as a tool, but it's an extremely convenient tool. It's really a very, very convenient tool, as I hopefully will be able to indicate. And so a further term that I think, and in some sense, is one of the things that I really like most about this about this part is that it says that, okay, so here I'm saying that you can map from connective K theory to L theory, and the statement is there's no other way you can possibly do something interesting. So that is expressed as follows. Even if I think about it like non-functorially, and I only care about like the algebra C, then the statement is if I look at homotopy classes of maps between KU and LC, or homotopy classes between LC and KU, or homotopy classes between, say, the connective cover of L theory to KU, then all of these are zero. So in particular, this expectation was completely wrong. There is no integral map from L theory to K theory that could be an isomorphism after you invert 2, because if you take the zero map, you invert 2, it's still the zero map. There's really only one way you can map. And okay, that way does everything for you that you want. But in particular, there are no other ways of comparing these two things, just by evaluating on the simplest algebra that you could imagine. Okay, so that's the first term. Let me draw a corollary of this fact that that these two are isomorphic, and maybe I should add this is true for a real C-star algebra. So there's some formal trick that that one can use to prove this, and it relies on the fact that also in this article, Rosenberg, for instance, already observed that if you invert 2, the L theory groups and the K theory groups are naturally isomorphic, also for a real C-star algebra. If you don't invert 2, then not so much was known, and maybe at the end of the talk I will describe what is known. So now we can fully compute them. But at the time, I think it was not quite known how to express the L groups in terms of K groups. But after you've inverted 2, this was somewhat known. And so this result is in particular true also for real C-star algebras. And one of the consequences of this and this Davis-Lick picture on assembly maps is the following statement, that if you look at the real version of the Baum-Conn map, say maybe E underbar G, then this has the Baum-Conn assembly map, and maybe I want to invert 2 everywhere, so things are correct. Then I can look at the K theory of the reduced group C-star algebra, invert 2, and now what I can do is I can use this transformation tau, and because it's natural, it induces an equivalence of assembly maps, if you will. And I can look at G equivariant L theory of the reals, map it to this guy, and then look at the Farrell-Jones map, so to say, for this function, which will also land inside here. But this has the pleasant feature of, by virtue of L theory being purely algebraic, it really factors through, apologies. This assembly map in L theory factors through the L theory of the ordinary group ring RG, and not the completed one, yes, which is the group C-star algebra. So this I refer as the Farrell-Jones map. These maps are isomorphisms because tau is an isomorphism after inverting 2. And then there's something that you can do. You can look at the integral version instead of the real version. And you at least get a commutative diagram like this, I guess, LZG 1/2. And let me be specific. So if you think about forms, then you learn, I guess, in a linear algebra course that if you have a field, say, in which 2 is invertible, then symmetric and quadratic forms determine each other. Every symmetric form has a unique quadratic refinement. So quadratic and symmetric forms are the same. Over rings where 2 is not invertible, that's not the case. And you have to distinguish whether you talk about quadratic forms or symmetric forms. Not the same datum. And what is relevant in surgery theory are these quadratic groups. These are the surgery obstruction groups, and it's really somehow classically phrased for quadratic L theory to consider the Farrell-Jones map. Although at least, I don't know, for torsion-free groups and regular rings or something, the quadratic and symmetric thing are equivalent. So you could also phrase Farrell-Jones for symmetric L theory as the same content. And then it's a non-trivial result that you have to believe me that on the left-hand side, you get an isomorphism. And if you believe in the Farrell-Jones conjectures, which I know have been proven for many groups, and in this picture, somehow the ring is always a dummy variable. So you really prove it for a group, it has nothing to do with the ring. If you prove it for a group, you prove it for all rings. I don't know of a single example where one knows the Farrell-Jones conjecture for a group, but not for like two different rings. This doesn't happen. So if you believe in the Farrell-Jones conjecture, then let me write Farrell-Jones implies, the Farrell-Jones conjecture implies that this right-hand side is also an isomorphism. Yeah, because Farrell-Jones would predict that to be an isomorphism and that. And so this maybe also is. And as a consequence, you obtain the following result that if the Baum-Conn map is injective after inverting 2, then so is the Farrell-Jones map after inverting 2, also injective. Now let me go through this. Why is that? Well, this, okay, I care about this map being injective, and it's injective if this composite is injective, yes? I guess we all agree that if a composite is injective, then the first map is injective. But this composite, by virtue of this commutative diagram, I can sort of compute by this composite. And that's essentially that map up to isomorphism, yes? So some of this composite is up to isomorphism, just the Baum-Conn map. So the Baum-Conn map being injective after inverting 2 is just strictly, a priori, strictly stronger than the Farrell-Jones map being injective after inverting 2. And I almost don't dare to say this in front of an audience of experts in C-star algebras, but to me it was always somewhat cumbersome that the injectivity of the Baum-Conn map after inverting 2 or rationally implies the Novikov conjecture. So the Novikov conjecture to me is really a statement about sort of homotopy invariance of higher signatures. I mean, to me, this is literally a statement about L theory. This is a statement about L theory, and it is somewhat cumbersome to a naive person as myself that Baum-Conn has something to do with it. And my main confusion arises from the fact that all the approaches to the Novikov conjecture coming from the analytic side, of course, use the signature operator on a manifold, and the signature operator is somewhat awkward in the sense that, for instance, if you compare it with the spin-Dirac operator, this is sort of a supernatural thing, which leads to, for instance, a very nice genus map from spin Bordism to K-theory. Yeah, but the signature operator does not lead to a genus map from oriented Bordism to K-theory. It just doesn't, and it only does so after inverting 2, and so in some sense, of course, it's not much of a surprise, but I was personally very happy when I learned this perspective that there ought to be this comparison diagram, which gives an a priori reason why Baum-Conn being injective just implies Farrell-Jones being injective, and that is more or less, like, by definition, the Novikov conjecture somehow. Okay, so I kind of enjoyed this perspective when I was young and growing up. Okay, so let me also indicate, because I think it's kind of interesting that if you believe in both the Baum-Conn conjecture and the Farrell-Jones conjecture, you have to believe in the conjecture that this map is an isomorphism. So you can look at just the group ring RG and you can complete it. It's well known that this map is not an isomorphism integrally. So if you don't invert 2, it's not. Somehow these conjectures say after inverting 2, this map is an isomorphism. And it's one of the things that, I mean, until today really puzzles me about L theory. So L theory is a functor that doesn't see the topology at all. It's a purely algebraic thing. And somehow it behaves surprisingly well with completions. In a sense that, for instance, you know, the fact that the K groups and the L groups are isomorphic, as was proven by Karoubi, Rosenberg, and Miller, implies that the L theory group doesn't change if you tensor with the compact operators, yeah, or maybe Kunz's O-infinity algebra. And for the compact operators, this is really, and we can think of the compact operators also as being exhausted by the finite matrix algebras. L theory is well compatible with passing to matrix algebras. That's sort of something purely algebraic. But then you pass to this completion of the infinite matrix algebra to get to the compact operators. And L theory doesn't see the difference between the two. Yeah, this is just a fact. It is true, but I still haven't fully absorbed why this really is. And somehow this is yet another instance, perhaps even more drastic instance of this extra property that L theory apparently has, that you stick in a hyperbolic group, Baum-Conn is known, Farrell-Jones is known. And so for a hyperbolic group, the completion from RG to the reduced group C-star algebra induces an isomorphism on two inverted L theory. And I don't know any other way of proving this than sort of this kind of argument. Doesn't mean anything, I guess, but I mean, it means what it means. Okay, anyways, so this is something I wanted to say. So before sketching how one can prove things of this kind, I wanted to move on and tell you that now we sort of know more. This is due to a theorem of myself with Thomas Nikolaus and Markus Schlichting. And it basically improves on the earlier result to say that we can also compare K and L theory for real C-star algebras integrally. So let me spell out what this means. Statement is that maybe there's again two statements. So A is that there exists a unique, lax, symmetric, monoidal transformation, call it again tau, from, I'll write it little ko, so that refers to real K theory of real C-star algebras to L theory. It's functors from real C-star algebras to spectra. And the induced map, and I mean, this is sort of, in some sense, the correct way of thinking about things, I suppose. So if I take ko of A, this is naturally a module over little ko, which is the value of this real K theory functor on the reals, and I can tensor it with L of R. Yes, because ko to L of R by virtue of this map tau being lax symmetric monoidal, that's a ring map, so I can base change. And there's a comparison map to L of A, and the statement is this is an isomorphism. So this is a spectral way of writing the L theory spectrum integrally in terms of the K theory spectrum. So let me phrase it on the one hand side like this. As a second perspective that I also like is, I've told you here that if I invert 2, I can express L theory directly in terms of K theory. I mean, just after inverting 2, they're the same. And so I can wonder if I can also express the 2 completed L theory, so where I focus on the 2 torsion problems, whether I can express that also in terms of K theory. And it turns out that there is a map to little ko of A to the upper Tate C2. So this Tate C2 is somewhat a spectral version of ordinary Tate cohomology on abelian groups. So if there's a version of Tate cohomology with coefficients in spectra, there is a canonical comparison map from L theory to the Tate construction on topological K theory, and the statement is this map is an equivalence. So you can also express the 2-adic L theory spectrum in terms of topological K theory, but you have to take a Tate cohomology with respect to C2 acting by, and in this case, it acts trivially on KO of A, of the trivial action, take cohomology of that. Okay, and maybe just to highlight what you can sort of prove from this description, you can just give a presentation of all the L groups. So, okay, this is nothing new. K0 and L0 are isomorphic. L1 of A is described as the co-kernel of the map eta from KO0 of A to KO1 of A. So apologies if I write K or KO, I always mean the same thing. And in both cases, it's just the topological K theory functor applied to a real C-star algebra. Yes, so if I ever map this out. Okay, so these real C-star algebras, they're K theory, they're canonically modules over just, the K theory of R. Topologists call that KO. And the homotopy groups of KO are sort of more interesting than the homotopy groups of KU. They have Z's in degrees divisible by 4 and Z mod 2's in degrees of the form 1 and 2 mod 8. Yeah. So in particular, there's this element eta in pi 1 of KO, and you can look at the action of eta on the K groups, and the statement is L1 of A is described as the co-kernel of this map eta.
There's a question about B in the theorem. In B in the theorem, there's a question in the chat about whether you need to complete the right side as well.
You don't, it's automatically two complete. So the statement is if you take Tate cohomology of anything that's bounded below, it's going to be a two-adically complete already. Yeah. You may, but you don't have to because it's already two complete. Yeah, so a different way of saying this would be that the map from L theory to this guy, because this is two complete, factors through the two completion, and then becomes an isomorphism. I should have said this. Apologies. Yeah. Okay, so L2 can be described as a kernel of Ada, but now something interesting happens. It's not the kernel of Ada with something that has to do with 2, but rather with KO6 of A mapping to KO7 of A. And L3 of A is naturally isomorphic to KO7 of A.
There's another question.
One way to think about this is to say L theory is for, okay, in general, I should have also said this for a real C-star algebra, L theory is not 2 periodic, it's only 4 periodic. And so you're secretly allowed to think about L2 and L3 as L-2 and L-1. And then you can use that K theory is 8 periodic, and so 6 and 7 also secretly are -2 and -1. If you prefer, then this is a perspective you can have. But regardless. So, okay, the statement is that you don't have to use this spectral description of the L theory spectrum to prove these results. But people haven't proved these results earlier, and the spectral statement is a convenient way of proving this.
There's another question in the chat about whether stability of L theory with respect to completions also holds for Banach star algebras that are not C-star algebras.
Yeah, I mean, I don't even know in what sense L theory really is invariant under completions, even sort of for like sub-C-star algebra, or non-complete sub-algebras in a C-star algebra. I mean, there are some instances in which this is known, and I cannot even tell you there when exactly it is true, and I have no clue what happens for Banach algebras. I mean, like, the situation doesn't become better or worse. It's just, I think the question of how L theory interacts with completion is just mysterious. Full stop. At least to me. Be happy to understand this better. Okay. So, okay, these are the statements that we now know about K theory and L theory. And I want to, because this is a conference also about homotopy theory, I want to indicate some of the things that maybe are surprising. So I want to indicate a little bit about this, and then I want to indicate how to prove something like this. And only if you're interested, and maybe after the talk, I would have intended to explain a bit more about this perspective. I'm happy to do so if time permits, but I kind of wanted to focus on these perspectives first. Although somewhat, this is the definite theorem, yes, this implies everything else. This result implies everything else. Okay. Maybe I should have added here then again tau 1/2 is an equivalence. And in particular, for instance, this implies that if you take the topological K theory spectrum, you invert 2, then as an E infinity ring, this is isomorphic to the L theory spectrum of the reals after inverting 2. And the same holds true for the complex case. Yes, so KU after inverting 2 is as an E infinity ring equivalent to L theory of C after inverting 2. And I believe that any of these highly structured results were, I mean, like strictly out of reach before we used these KK theoretic techniques to prove these results. Okay, so let me indicate some proof ideas. So let me indicate why is LCKU equals 0, and this argument will imply the same for all the other variants. So there are several ingredients, and one ingredient is something that's called Anderson duality. So the statement is that there exists a spectrum called the Anderson dual spectrum of the sphere. And you can define the Anderson dual of any spectrum as just the mapping spectrum from X to the Anderson dual of the sphere. And then there exists a short exact sequence that describes the homotopy groups of the Anderson dual of any spectrum. In terms of, I guess, homs out of pi minus n of x to z, and x of pi minus n minus 1, hopefully. I think that's true. Okay, so there's sort of a universal coefficient theorem for this Anderson dual, the homotopy groups of the Anderson dual of something. So let me not go into the definition of the Anderson dual, but focus on, I mean, by definition, you can observe that, so here's a fact we'll use, that the Anderson dual of Ku is equivalent to Ku. Let me say in words why this is not super surprising. So this perspective says that because Ku is a ring, if you map Ku into something, that's naturally a Ku op maybe, but okay, a Ku module. And if you have a spectrum, which is a module spectrum over a ring, and as a module, the homotopy groups are free of rank 1, then the spectrum is in fact free of rank 1. That's sort of because you can map in and check on homotopy groups, it's an isomorphism. And it's not so difficult to prove that from this picture that the Anderson dual of Ku has homotopy groups free of rank 1 over Ku star, and so this must be equivalent to Ku. And the same applies to L theory of C, because the homotopy groups formally look the same. I haven't really said this, but kind of the same argument is also true for the complex numbers, L of C. There's also Anderson self-dual. And so what you can do is you observe that the mapping spectrum from L of C to Ku, that's now the mapping spectrum from L of C to the Anderson dual of Ku. But the Anderson dual of Ku is itself the mapping spectrum from Ku to the Anderson dual of the sphere. So just by junction, you see that this is the mapping spectrum from L of C tensor Ku to the Anderson dual of the sphere, which in turn is the Anderson dual of L of C tensor Ku. Okay, so this sequence then pops out to say that maps from L of C to Ku, which are secretly pi 0 of maps from L of C to Ku, is the same thing as pi 0 of the Anderson dual of something, and then I can use this coefficient formula to see that this is homs from L of C tensor Ku. Oh, sorry, I should maybe write it like, allow me to write LC0 Ku. So by that I mean the zeroth homotopy group of the tensor product to Z. And the kernel of this map is then X of LC minus 1 Ku to Z. Okay, that's just sort of a basic computation. And now there are two facts one uses. The first fact is sort of somewhat easy, is that LC tensor Ku is an even spectrum. So it doesn't have any odd homotopy groups. And in particular, this means this term is 0. And the reason for this is that, so if you want to compute LCKU, then you can use something from homotopy theory that is called the Landweber exact functor theorem, that says that you can compute the K theory groups of any spectrum as the mu homology tensored over mu star with Ku star. And okay, this is sort of Landweber exact functor theorem. But this is even, Ku star is even, so it really suffices to prove that that guy is even. Because if I tensor something even over even with even, then sort of some Tor spectral sequence will say, I mean, I don't know, this is purely algebraic tensor product. Even tensor over even with even is even. No contributions of anything odd ever happening. And then L of C itself is 2-periodic with no odd homotopy group. This implies that it's what it's called complex orientable, and so there is an isomorphism, the Thom isomorphism, that says that the mu homology of LC is the same thing as the LC homology of BU, but this guy has even homology, even integral homology, and so by an Attila-Hirzebruch spectral sequence, you see this is even. Okay, so that's like a combination of a number of things, but in some sense, sort of in like stable homotopy theory or somewhat standard techniques using this Anderson duality, computing this short exact sequence, and then using the fact that KU is lambda exact and LC itself is even, that the tensor product is even. Okay, that's first fun fact. And the second fun fact, and this is really where something geometric enters the picture, is the following result, is that the canonical map from LC to LC tensor U to LC tensor KU, and then you invert 2, this map is an isomorphism. And the reason is that for any spectrum, there's a pullback diagram where I look at this and I localize and I rationalize. So there's a pullback diagram of this kind, so it really suffices to prove that this map is an equivalence, or in other words, to prove that this spectrum is rational. But then you sort of, I mean, just sort of 2 localization is something that commutes with tensor product, so that's the same thing as 2 localizing L of C. And then there's a geometric fact. This geometric fact says that there is a ring map from MSO to L theory of the integers. Sort of that assigns to a manifold somehow its L theoretic signature. This is something that is perfectly well defined. Whereas sort of sending a manifold to its signature operator doesn't lead to a ring map from MSO to K theory. Yes, sort of the signature somehow naturally as a spectrum valued invariant lands in L theory. So you have this, and then there's a homotopy theoretic fact, that says that there is a ring map from HZ to MSO after localizing at 2. So this is E infinity for those that are interested. This is, I believe, at best E3. One can make it E3. I think one cannot make it better than E3, but at least it's a ring map. And this implies that L of A, 2 localized, is an HZ module. And this implies that this guy is a module over HZ tensor KU. And that's sort of, again, another homotopy theoretic fact is that this spectrum is rational. Different perspectives on this. I'm happy to answer this either if someone asks specifically now or later if people care about. So this is just sort of a fact from homotopy theory that if you take the integral homology of periodic KU, you get something rational. And there are different perspectives on why that is true. And none of them are trivial, but none of them are like super hard in homotopy theory. Okay, so this means that this thing is already rational because it's a module over something rational, and so rationalizing doesn't do anything. So this map is an ISO, and hence this map is an ISO. But that means that I'm allowed to snuggle in like a 2-inverted thing here. So all of a sudden, this Hom group becomes a Hom group from some uniquely 2-divisible group to Z, and there is no non-trivial map from a uniquely 2-divisible group to Z. Yeah, it's sort of a basic algebraic exercise. So secretly, that is also 0. And that's sort of what enters. So this is really there's a number of things that go into this computation, but it's a fact that there's just no way to map these periodic versions of L and K theory to each other before inverting 2.
So do you have any analogous results in the real case? Because a bunch of facts used about KU are a little different.
Yeah, that's true. And the same statement holds true. You will use something slightly different. So KO is not Anderson self-dual. It's only Anderson self-dual up to a shift, but that's going to be sufficient. And what you can prove is that this fact is still true. And I believe this fact is still also true because of some retract argument you can give. Yeah. Okay, so the statement is the exact same statement is true for the reals, and the proof is somewhat of a combination of the same argument plus reduction to the complex case. Yeah, if you're interested in the details, this is spelled out in this paper with Nikolaus and Schlichting. Sort of there we make this explicit and give the exact argument. And I hope this argument is correct. Okay, so that's what I wanted to do. Okay, so let me try to sketch how you prove these results, that there's these maps and why are they isomorphisms and so forth. this theorem of Karoubi, Rosenberg, and Miller, it implies that L theory factors through KK. Sort of there's an essentially unique extension L through KK, because KK is defined as, I mean, okay, I defined it, or I mean, Uli explained to us that we can think about KK as an infinity category as the Dwyer-Kahn localization at the KK equivalences. But in order to check whether or not L theory sends a KK equivalent to an isomorphism, I have to check on homotopy groups. But the homotopy groups are isomorphic to K theory. And of course, K theory does send KK equivalences to equivalences. Yes, so L theory also sends KK equivalences to equivalences. And the decisive fact that you prove is that this functor, this sort of a functor, this is, it's split exact, and in particular, it preserves products. But what is not true is that this functor commutes with fiber sequences. Yeah? So this category is stable, this category is stable, but this L theory functor doesn't preserve finite limits. It only preserves some finite limits. Those that come from short exact sequences of C-star algebras that come with a multiplicative split. Yeah, not a CPC split or something, with an actual multiplicative split. Those short exact sequences L theory will preserve, but in general it will not. And sort of a basic Yoneda argument says that because K theory, little K theory, is the sort of the mapping connective spectrum out of KK, out of C, as a functor from KK to connective spectra. Yoneda says that there exists this unique transformation from K to L. Yes, I mean, I should have said, so this is lax symmetric monoidal, and then this functor is also lax symmetric monoidal. Yeah, the localization sort of preserves this property of being lax symmetric monoidal. And then there's a completely formal argument that the Yoneda functor out of the tensor unit is the initial lax symmetric monoidal functor. That's just a purely categorical argument that in one categories you prove as an exercise, and in infinity categories it's not an exercise, but a correct result. I mean, it depends what you think, but okay, in any case, so this is what you have. And in fact, something slightly more is true. In fact, what you see is that the space, well, let me write it like this, the space of natural transformations between the, sort of in this functor category from KK to spectra, from K to L, this is naturally isomorphic to L of C. Yeah, this is what the Yoneda lemma says. And if I apply pi 0 to this, so I look at homotopy classes of natural transformations, then I get L0 of C. And if I do this, then I observe that the same statement says that this is maybe the homomorphisms in, I guess, the category functors from KK to abelian groups between the little k naught functor and the L naught functor. But again, by Yoneda, yes, because in sort of the category KK, pi naught is also, I mean, yeah. Okay, good. So in particular, this means any natural transformation that I have here uniquely lifts to a natural transformation from K to L as a spectrum valued functor. And this identification is made in a way such that I recover this guy by passing to pi 0. So statement is this composite is obtained by passing to pi 0. And that map is an isomorphism. So anything I can write down on K0 to L0 is in fact refines to a spectrum valued thing. And so you can just take the Karoubi, okay, let me write KRM iso from K naught to L naught, this natural isomorphism, and lift it. Lift it to a map from K to L by this result, yeah? There's a unique natural transformation up to homotopy that does the isomorphism on K0 that you already know. And then it's a little check. So little check. This agrees with this unique natural transformation tau that you get from the Lex symmetric monoidality. This has to do with the fact that tau in here goes to the unit element in the ring L0 of C for formal reasons, and you just observe that this transformation you write down also goes to the unit element, sort of by construction. And then by means of this equivalence, these transformations agree. So in other words, what this tells us is that there's this unique transformation, and I already know that it induces the familiar isomorphism from K0 to L0. And then what you do, so to compute, let me just finish by explaining this, to compute the effect on pi 1, say, of tau A from K of A to L of A, you do the following trick. So let SA be the C-star algebraic suspension. So in KK, in the stable infinity category, S is somehow the loop functor. That was also something that Uli explained in the very first of his 2 lectures. Okay, so you have this. And then for formal reasons, there is a natural map from the suspension of S of A to L of A. And sort of this map that we've constructed, it commutes with this. So there's also something like this. So this is tau, and this is also tau in some sense. And the statement is, well, K-theory is excisive, so it sends this lower thing to an isomorphism. And if you apply pi 1 here, then pi 1 of that secretly becomes pi 0 of those two. Yes, the pi 1 of the suspension becomes a pi 0 of the other thing. So on pi 0, I already know that this map is an isomorphism. And so that means this map is really described in terms of this map. And then what you do is you sort of the lemma is give a formula for the cofiber of this map. So this is cofiber given by the 0th reduced K group, and then you take Tate C2. Maybe not reduced, I'm not sure. To be honest, actually non-reduced, I suppose. Okay, so that's a non-trivial result you have to use. But once you have that, you can analyze sort of what happens on homotopy groups. And that's sort of the basic ingredient. And it really proves, you know, that if 2 is invertible, the map is an isomorphism. If you invert 2, the map is an iso, and all the things that you want. Okay, so thanks very much for the attention. I will stop here.
Great, let's thank the speaker. And if there are any questions, the floor is open.
So I think there's a question in the chat. Can the Baum-Kahn or Farrell-Jones assembly be somehow categorified like the geometric topology one has been by Bartels and Nicolaus?
And, say that again.
Maybe it's easier to pull up the chat, but it says, can the Baum-Kahn or Farrell-Jones assembly be somehow categorified like the geometric topology one has been by Bartels and Nicolaus?
Yeah, okay, so I guess Bartels Nicolaus say how to interpret categorify the K-theory assembly, the algebraic K-theory assembly map of a space. So this is a slightly different flavor of assembly map. That analog in L-theory also exists. So there is almost surely an analog that says that the assembly map in L-theory, but sort of in a slightly different flavor than the one that we're looking here. Sort of here, the assembly map is sort of based on a group. In the Bartels Nicolaus stuff, the assembly map is based on a space. So you have a functor on spaces, and that you assemble. Yeah. So that variant in L-theory has a categorified version. But I think maybe more interestingly is that this picture of the Kasparov way of thinking about the Baum-Kahn map can be translated categorically, I think, now. And you can have a sort of a similar picture of describing the assembly map in algebraic K-theory in a similar spirit than sort of the one that you know from Baum-Kahn using Kasparov KK, equivariant KK theory. And, yeah, I don't know if that answers the question, but
there any other questions?
Why is your fact true? So H of C tensored K of U is rational.
Why is HC tensored KU rational?
Rational.
Yes, okay. Why is that? Think maybe. Yes, okay. Okay, so it suffices to show that HC tensor KU is rational. So is rational. That's equivalent to proving that it vanishes modulo P. Yes, because that means all primes are invertible. But if you model by P, this is just HFP tensor KU. Or equivalently, this is 0. Okay. Let's try to compute that, and let's try to use Snaith's theorem. So Snaith says that you can think about KU as the suspension spectrum of CP infinity. I'll write that as sphere adjoint CP infinity, and then you invert the bot element. So in CP infinity, there's the bot element. You can invert it, and you get KU. And now I think the decisive fact is that if you look at the HFP homology of KU, what you then get is the HFP homology of sphere adjoint CP infinity. I mean, I think this is more commonly known as the homology of CP infinity with FP coefficients. And then you invert an element in degree 2. Yes, the bot class has degree 2. But it's somehow well known that because CP infinity is a topological group somehow, this implies that this guy has divided powers. So that means on the integral homology of CP infinity, if you take an element to the pth power, it will become divisible by p. And that means that has divided powers over z, and hence over fp, it implies that any class is nilpotent. Any class of positive degree is nilpotent. And so if you invert a nilpotent class, you get 0. Yeah, that's one way to think about it. I think Anderson and Hodgkin just computed somehow the K-theory of Albert-MacLane spaces and then pass to a limit. You also see that somehow this becomes rational, but I think this stable argument is in fact much simpler. But this was sort of known like a long way back from the computations of the K-theory of Albert-MacLane spaces, I suppose.
Okay.
Any other questions? Okay, let's stop the recording then.